So in this video, what we're going to do is parameterize a rectangular relation. So we're going to start with something that's in rectangular form and convert it into a parameterized form. So parameterizing is pretty simple. The simplest possible thing that you can do when you're parameterizing a function is to take the input variable and set it equal to the variable name you want to use to parameterize. So the simplest possible case. And you would do this if you didn't have any conditions that you were trying to meet, any restrictions that were being imposed on you. If you just need to parameterize it, you say, hey, let x equal t. It's super simple. Let x equal t. And then if you do that, you know that y is going to equal. Now you go into to the function or the relation, and everywhere you see an x, you replace it with a t. And there's a perfectly legitimate parameterization of this. I didn't have any conditions I was being asked to meet. I wasn't being asked to say, hey, when t equals 1, we want the ordered pair to be, 1, 1 or anything like that, or 0, 1. We weren't given any, nothing was specified. We weren't told to meet any conditions. So this is the easiest way to do it. And I have found in practice that this is usually the way that I most frequently do it. I don't usually need to do it a different way than this. But remember, we said that there's infinitely many ways to parameterize something. You could just as easily have said, hey, let x equal the opposite of t would be perfectly legitimate as well. And then you would just go in and everywhere you saw an x, you'd replace it with the opposite of t instead. And if we did that, we'd get y equals the opposite of t squared minus the opposite of t plus 1. This is also a legitimate parameterization. We can let x equal any scalar multiple of t that we want, and it's a parameterization. And some questions that we should ask ourselves if we do parameterize, say by putting in the opposite of t instead of t, is does that change the direction of movement on the parameterization? Because remember, a parameterization always has a directionality with it. And we've seen that in the previous videos now. Every time we've graphed a parameterized function, we've put the arrows on it indicating direction. So a good question to ask yourself is, if I wanted to reverse the direction of motion in a parametric equation, how would I do that? And that's something that you should take some time to think about. Here's another possibility. It's kind of an interesting thing to do. You can say, hey, let's parameterize the function we want to parameterize by using the derivative of the function. So parameterizing a function in terms of its own derivative. And remember, a derivative, dy dx, is just tells you the slopes of the tangent lines to the original function. So it isn't uncommon to use m to represent slopes, so that's what's happening here. So if we look at y and we take its derivative, we know its derivative is 2x minus 1, and then we just give that derivative a name. We say, hey, we're going to let the derivative be m. M is 2x minus 1, the derivative of the function. I could then solve this for x, right? We could add 1 to both sides and then divide both sides by the 2. That's a coefficient on the x. And now I have a parameterization of x in terms of the derivative of y. M is just a variable sitting there. And then, of course, if we do that, now we have a parameterization that has x equals m plus 1 over 2. And then we would just need to go into y, and everywhere we see an x, we replace that x with m plus 1 over 2. M plus 1 all over 2. M plus 1 all over 2. And of course, the 2 down here would be squared. So I could rewrite this as m plus 1 squared over 4. And maybe we could think about cleaning this up a little bit. So for example, if I factored out of 1/4, then that would leave me with an m plus 1 quantity squared right here. And if I square out an m plus 1, I'm just going to get m squared plus 2m plus 1. And here I would have a minus 2 times m plus 1, because when I distribute the 1/4 in, I need a fourth times 2 is a half to get my 2 in the denominator. And here I would need this plus 1 to be a plus 4, so when I do a fourth of 4 I get my 1 back. And then I could just clean things up a bit. This is m squared plus 2m plus 1 minus 2m minus 2 plus a 4. And what's that going to do? It's going to give me an m squared. 2m minus 2m is 0. And we get 1 minus 2 is negative 1. And negative 1 plus 4 is 3. So we get m squared plus 3 if I didn't make an algebraic mistake. And this is all supposed to be times the 1/4. I don't want to lose my 1/4. So here I have another parameterization of this rectangular function. So again, we looked at an example of it in video 2, that there is more than one way to parameterize any rectangular function. The options are limitless. Again, this is the simplest way to do it right here, and probably if you just need to parameterize something and don't have any conditions being imposed on you that you have to meet, then that's usually the go-to parameterization.